All right, here we go. The first one, did you say converge or diverge or what? Diverges because it's the harmonic series. Could you also identify it as a P series and then done all that stuff?
Yeah, sure.
You could. I would take it, but I prefer you know the vocabulary of harmonic, all right? This guy, converge or diverge? Converge. This is a P series. Identify P. P is? 2. Identify the test value, which is 1. How it refers to 1. This is greater than 1, so this converges. That's what the work should look like. If it doesn't look like that, get out the eraser and make it look like that. All those things are necessary. Reporting P, testing it against 1, identifying it, converging, diverging, obviously the question. All right, what about this? Is that a P series? Maybe. I like it. That's true. It's maybe. It could be a P series with a little work. It is not a P series in its current form, but is this the sum of 2 P series? Yes. Okay, so that's the strategy there. You do nothing the way it is. You rewrite it as a sum of 2 P series. Then you work each one. The first one is a P series with P equal 2 greater than 1, so it converges. Excellent. The second one is a P series with P equal 3 halves greater than 1, so it converges. The sum of converging plus convert. Hi.
Mr. Bell, do you have a spare pencil? I mean, sister. Sorry, I know. Now you're grossly insulting Mr. Bell has broken desks outside his room.
I saw that. He must have gone
Yeah,
off on
got
something.
violent. Thank you very much.
Sure, no problem.
Sorry, Mr. Rick.
No problem. No worries at all. So converging plus converging is converging. The sum converges.
No, it's serious.
You with me? Are you with me?
What if they would have been different? Would you just say divergence?
If one of them diverges, then you'd say the sum diverges. Finite plus
For example,
right? Yeah, finite plus infinite is okay. All right. Speaking of finite and infinite, let's talk about 2 huge tests: direct comparison test and integral test.
You said we wanted to have a test.
There's 2 tests. All right. So you don't need to write this down, but typically you're going to be given a series problem, and you'll have, it's kind of like a programming kind of thing, in that you'll just make all these decisions along the way. The very first thing you do is the nth term test or the divergence term. Does it even have a chance? And if it's a yes, then you continue on saying, all right. Then you'd say, is it a known series, like a P series or geometric or a telescoping? And if it was, you'd go that way. But if it wasn't, then you might use a series or several other tests, like a direct comparison test, or the integral test, or the ratio test, or the alternating series test, or all these other series of tests. Now that then is the side we're on now. We're past known series and we're into sort of like a known series. All right? What do you do? Well, by way of introduction, let's go to this. What if I asked you for the area under 1 over x squared, which is a rapidly decreasing function? It decreases a little more quickly than 1 over x from 1 to forever. That's an unbounded region. Now we could go at that area 2 different ways. In a Riemann sum way, now that would be infinite right-hand rectangles, or an integral. Now if I used right-hand rectangles, all of 1 unit wide, then would that right-hand height mean smaller rectangles or greater rectangles than the true? Smaller. The right edge, because it's decreasing, the right edge will be less than the left edge, and we're going to be under the true area a little bit. That's okay. The first, for the Riemann sum, I want to compare Riemann sum to the integral. Now the Riemann sum, the bases of all rectangles, they say go with the delta x of 1. So I'm going to have a base of 1 unit for each by their description. And the heights. What's the first height? F at 1 or F at 2? 2. It'll be 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and it would go further. Now if we compare that to the integral, it would be the integral from 1 to infinity of 1 over x squared dx. If I were to rewrite the left-hand side Riemann sum in a series notation, the 1 I could dump. And the rule for the series, what is the rule, or the general rule, general term for the series? 1 over n squared. Now I don't use x squared because in series problems we use n to represent real numbers, whole numbers rather than integers. What does n start at? 2. Now that is not perfectly like the integral because it starts at 1, but in every other fashion they're pretty much the same rule, right? Same function, just different variable and a little different starting point. Now, we said, actually, let's just chill this one out for a second, let it ruminate. Let's talk about how these two we compare. You said the Riemann sum is less than because the rectangles are below the curve, yeah? And if we were to find the value of this, I'm going to write this as x to the negative 2. Then that series would look something like, what's the antiderivative of x to the negative 2? Power rule, baby. A, raise it by 1, divide by the new. Negative 1 over x from 1 to a. The limit as a goes to infinity of negative 1 over a minus, or plus rather, 1 over 1. So does that infinite area converge or diverge? It converges to 1. What does that lead me to say about the series then? We said the series is less than the integral, and the integral has a finite sum. Therefore, the series must converge. Okay? We could conclude then that the series must converge as well. Now this actually is an introduction of both series ideas. The direct comparison test is a way of saying, well, less than finite is finite, and it must converge. Greater than infinite is infinite, and it must diverge. That's really the direct comparison test, and I'll show you that in a minute. The integral test is a little like we did here. If I can compare a series to an integral of the same function, then they have to behave in similar fashion, converge together or diverge together. It can't be the case that the series converges while the integral diverges. It cannot happen. I will say this just in passing. What if it had been left-hand rectangles? If it had been left-hand rectangles, then would the series be greater? Or, sorry, the left-hand rectangles would look like this, yeah? In left-hand rectangles, the series would have started with 1 over 1 squared and 1 over 2 squared and 1 over 3 squared. Our series would have been the same rule, but starting at 1, and we would have said it's greater than the integral. Right? Do you agree that the left-hand sum is greater than the true integral value? Oui. All right. We said this is 1. From that, what could we conclude? The series, does it converge or diverge? The series is greater than 1. It's worthless. That tells me nothing. It could be finite. It could be infinite. This is inconclusive. Greater than finite tells you nothing. It could be infinite, it could just be a bigger finite. So sometimes the direct comparison test fails because we don't know one of two conclusions. Greater than finite is inconclusive. Less than infinite is inconclusive. I'll talk to that in a second. Here we go. This I don't feel like adds anything, so never mind on that. Let's go to the integral test. The integral test goes something like this. If an integral of the same rule or function of a series convert of a if an integral of the same rule as a series, that's what I was going to say. Converges. No, I don't like what I'm saying here. Can you erase that, please? I'm going to try again. Oh, don't give me your. Okay, let me go this way. If an integral, let's actually add one more, okay? If an infinite integral and an infinite series use the same rule or function, then they must converge or diverge in the same way. Which is to say, if you can show that the integral converges, then you can conclude the series converges. And if you can show that the integral diverges, then you can conclude the series that's just like it must diverge. Be careful though, don't go too far with this. The series and the integral behave the same because they have the same function. You're talking about the same rule here, whether it be 1 over x squared for the curve or 1 over n squared for the series. There's the same rule, but they don't use the same kind of numbers. The integral uses all tiny little numbers, real numbers, whereas the series uses whole numbers only. So yes, they converge in the same way, but they don't converge to the same thing. The sum of the integral will not be the same necessarily as the sum of the series. So when I say, however, be careful, the series uses integers only, and the functions for all real numbers, they don't converge to the same value. So don't assume that because the integral had a sum of 1 in the previous problem, that the series would add to 1 also. Yes?
What if it's an equation like 1 over x squared where there's a vertical asymptote of 0, so if you did the summation, it wouldn't like count that, so it's just at 0. There is no point.
You're right. So that actually is a little more complicated, and we haven't even talked about what happens if in a series the rule isn't continuous over that domain. I'll come to that eventually, but not today. That's a good question. Yeah. All right, so this is what an integral test problem would look like. The question is, gives you a series, and they want to know if it converges or diverges. The first thing you should try is, or at least check, is the divergence. I should see at the top of every box this tiny little, it's not too much to write, just does this thing even have a chance? Do the terms go to 0? Because if you're adding infinitely many things that don't go to 0, there's no chance. Does this have a chance? All right. So the fact that the terms go to 0 tells you it might converge. Proceed on and investigate further. If it diverged, then that would actually be really beneficial. You wouldn't even have to waste your time with any test. You just say, oh, it has no chance divergence. All right. This has a chance, so we continue on. So now the question is, why integral test? What in this problem tells me I should use an integral test? Well, first of all, it's not geometric, so it's not a p-series, and it's not telescoping, so I've got to do something else. What makes this an integral test is this looks like something I can integrate. Now that could be a lot of things. Actually, integral test very powerful for you because you can integrate so many things. It's going to be an option in a lot of cases. Now, running the integral test then looks like this. You find a comparable integral of the same function. Same function, but use x, not n. So this would compare to the integral from 1 to infinity of 2x over 1 plus x squared quantity cubed dx. You see? Now I look at that and I think, yeah, I could integrate that pretty easily by use of. I definitely want to take the correct first step of making it a proper integral so your math teacher doesn't freak out on you. And you don't try and integrate love or something foolish like that. And now, what I would prefer is some kind of mental use of or scratch work use of. What is u? 1 plus x squared. What is du? Okay, so it feels like everything is going according to plan. Du is exactly what I want it to be, no adjustments necessary. What is the integral of 1 over u cubed, or u to the negative third? Negative 1/2, negative, right? Negative 1/2 u to the negative second. Oops. Wouldn't you agree that's the antiderivative? So taking back over here, I did it all off to the side or mentally, so I didn't have to get into the changing the limits and all that stuff. The antiderivative is 1 over negative 2, 1 plus x squared squared from 1 to a, I think. Do you agree with that? Do you agree with that?
Yes.
All right. If we evaluate the limit, then I get 1 over negative 2 times 1 plus a squared squared plus 1 over 2 times 1 plus 1 squared squared. What does the first fraction go to? As a gets huge, that denominator gets huge, so it goes to 0. And the other one goes to 1 over, let's see, 1 squared is 1, plus 1 is 2, 2 squared is 4. It converges to 1/8, yeah? All right. Now, here's where the series comes back into play. From that, we can make our conclusion. The infinite integral converged, and therefore the series must converge also. So the conclusion would say basically something like that. The integral converges, so the series that they asked about must converge also. You could say parenthetically by the integral test, but it's not necessary. And it's kind of accepted that you're using the integral test from your work. Okay, so you don't need to say by the integral test. You with me? Okay. Let's talk about the direct comparison test and show you what it looks like and what the word should look like. 1 over n factorial. That's not a geometric series. It's not a p-series. It's not something I could integrate. How do I tell if it converges? Well, you could use the direct comparison test. I am, in this case, telling you what to compare it to, but eventually you'll kind of just figure it out on your own. It goes like this, however. You're going to always take the one they ask about and figure out something that you know about, like its convergence or divergence, and compare the two. You know this one a ton about this. What about this series? What's it like? What do you know about this one? It's geometric, and does it converge or diverge? Converges, okay? Now my hope is that I will be able to show this is even less than this one. And if this has a finite sum, and that's less, surely this must also be finite as well, right? That's the thought process. So it goes like this. First, you need to establish or name what you're going to compare. Now, I kind of gave you that in the problem. But usually they don't tell you what to compare to. It's for you to know. So you'll say, hey, I'm going to compare this to, some people say versus, compare to 1 over 2 to the n. And you'll see me take a lot of liberties with 1 to infinity. I never had a professor ding me on that, but if my life depended on it, I would be like this. Okay? Now, you then show how they compare. Show inequality work. And it needs to be slowly. How can you make money? Okay? You need to, it's very much creating an airtight argument here. N factorial versus 2 to the n. Let's start there. Not the fraction, not the series. Just those two basic functions. Which is more powerful? Factorial is greater, because as you go on, you're multiplying by another bigger number, whereas this, as you go on, you're just multiplying by another 2. So you're getting bigger and bigger here. This is greater. Now, you wouldn't have to prove that, thankfully. You could start there. You're going to start obvious, and work towards the series slowly again. So the next thing you might do is say, what about when you take the reciprocals? 1 over n factorial. When you take reciprocals, would the n factorial be greater than n, or now would it be less? Less than. Now each term of 1 over n factorial is less than each term of 1 over 2. Well, what if you added all the terms? Wouldn't the sum of all those terms be less than the sum of all those terms?
At n equals 1, wouldn't n factorial be greater than?
That's, okay, so good point. So if, this is, you're pretty good. At what point is this one greater? For n when? When is this one greater? I think at 4, for n equal 4? Yeah. Oh, you're good. Nobody even saw that. They didn't even care in the last class. They just said, okay. Oh, you're right. For n, once you're beyond, okay.
Really?
Yeah, sure. For n, and you don't even have to say that, really. For n beyond 4, because that does require some thinking. But as n goes, typically you would say, as n goes to infinity, this is usually what goes through people's argument is, as n goes to infinity, n factorial is greater. But you're right. For n greater than or equal to 4, the factorial is greater. I like it. So for eventually, as we add more and more terms, the exponential, or sorry, the factorial series is less than the exponential series, yeah? The exponential series, we said it was finite. Well, if the one they ask about is less than a finite number, surely it must be less than a finite number, and so it must converge. That's then the conclusion. We would say something like 1 over n factorial converges because it is less than 1 over 2 to the n, which converges. Now, the only gotcha to this that people leave off and that you need to say is you need to justify why you say 1 over 2 to the n converges. Why is this convergent? Not P. Geometric with an R of 1/2, which is less than 1. You can't just say, hey, it's less than this other one which converges, take my word for it. You've got to say it's less than this one which converges because blah, blah, blah. All right? The conclusion is usually what the star of the show is. That's what's most read. It's kind of like the first derivative test. You need to do a ton of work to get there, but the conclusion is what you want to actually focus on. Are you with me? Would you go to this box here, however, and go to the definition and underline one word? This applies to positive term series. If, for example, the geometric series 1 over 2 to the n looks like this, it starts to, geometric series is a half, and then it adds a fourth, and then an eighth, and so on. So this geometric series starts to approach a finite limit, right? As I add more and more terms, what I'm adding is smaller and smaller. It starts to top up. Okay? You with me?
Yep.
All right. The factorial, it is less. After a certain point, it is less. And so if the red has a top floor, the blue must have a top floor or ceiling as well, yeah? As long as the series are negative. I mean, is negative 1 less than 1 over 2 to the n? Isn't every one of those terms less than 1 over 2 to the n? And yet, is this finite? If I add infinitely many negative terms, is it converging? So it's got to be the fact that it's a positive term to make sure that it's not infinitely negative. You with me? All right. Let's talk then a more typical example. And factorial is pretty rough. This is what one is commonly done. You get a series like this, and it's like a p-series, but because of the plus 1, it's not. If that's the case, then use the direct comparison test. The process then goes like this. You would say something like versus or compared to. What is this like? That you know something about. 1 over n squared, yeah? We're going to compare to 1 over n squared. Does that converge or diverge? Converge, all right? So I'm hoping that I can show that this one, do I want to show that this is more or less than my series for this to all work? Less than. If I show it's greater than finite, that doesn't tell me jack. But if I can show that it's less than finite, then it must be finite as well. So I'm shooting for less. We need to show that. Let's start off with something obviously true between the two, like n squared plus 1 is greater than n squared. And I'll pause here and say, I'm throwing you a bone. My professor made me start there. He said, you have to start with something a kindergartner can agree with, not something that an algebra student can agree with. I think that's ridiculous. I'm not doing this for kindergartners. We can all agree that n squared plus 1 is greater than n squared. Yes? All right. Now then, you want to gradually work towards how the series compare. I'm going to do that in 2 steps. Go to the reciprocal. 1 over n squared plus 1 must be less than 1 over n squared. The minute I take reciprocals, it behaves in the exact opposite fashion. And therefore, the sum of all these positive term series must be less than the sum of all those positive term series. So from that, I have demonstrated what I need for my conclusion. The series, you don't have to say a question, you could say the series 1 over n squared plus 1 converges because it is less than the series 1 over n squared. And I'll write that in, which converges. And then I have to say why. Why do I say 1 over n squared converges? Sorry, I need to give you a second to catch up. The series 1 over n squared plus 1 converges because it's less than 1 over n squared series which converges. And why does it converge? P series, it's not geometric, it's P series. P series, P equal 2 greater than 1. All right? What if the question had been, hey, the series 1 over n squared minus 1 instead of plus 1? Well, what about n squared minus 1? It's less than n squared, yeah? All right. 1 over n squared minus 1 would be greater than 1 over n squared. And the series 1 over n squared minus 1 would be greater than the series 1 over n squared. That would lead me in the direction of saying, hey, this series 1 over n squared minus 1 is greater than finite. And so what? What does that tell me? Greater than finite. It could be also finite, just bigger, or it could be infinite. So the direct comparison test fails. It's inconclusive. And that'll happen. In that case, you would use a different test, and you need to understand when something you tried falls apart. Yes?
But like, n squared minus 1 is greater than n to like the 2/3? Or to the 3/2?
That would be hard to, why would you do that?
To prove that it does converge? Because it does converge.
It does, but you use the limit comparison test, don't do that. Yeah, don't do that. Keep comparing it to something like that. All right, now, you can use the direct comparison test to prove convergence. You can also use the direct comparison test to prove divergence. Check this out here. 1 over n minus 1, what's it like? 1 over n, which converges or diverges? Diverges. So if we could show that this is what? Greater or less than 1 over n? Greater than 1 over n, then we'd be gold, because greater than infinite is infinite, yeah? So that's the hope. We're going to say this is like the harmonic series 1 over n. Let's get into the inequality work and show, hopefully, 1 over n minus 1 starts off as less than n. What's the next step in my inequality work? Take the reciprocal. 1 over n minus 1 is greater than 1 over n. And then the sum, 1 over n minus 1, is greater than the sum of 1 over n. So we showed that the series they ask about is greater than a harmonic, which is infinite. Greater than infinite must be infinite. So we conclude the series 1 over n minus 1 diverges because it is greater than 1 over n, which diverges. And why do we say it diverges? Harmonic. Okay? Or you could say because it's greater than the harmonic series.
So you can only conclude something if it's greater than infinite or less than.
That's exactly right. Okay, for positive term series. And alternating series are a whole other ball of wax we'll talk about later. But that's exactly correct, yes.
And then the other ones you just say the direct comparison test fails.
Yes, for now you'd say the direct comparison test fails and you'd kind of stop, but later on you'd go back and try some other test, but you don't know anymore. Okay? So you could see that this would have failed because it would have been less than infinite. You can just write that. Less than infinite is inconclusive. Okay? Would you go to the homework then? Box 9, please. This one's slightly different than the book box 9. I like this problem better. So would you do this problem in box 9? Say, does this problem converge or diverge? And justify. What do you mean, yikes? Start here, by the way. terms do go to 0, so it has a chance. Are you seeing it converge or diverge? I would say the series they give me must diverge because it is greater than, then you identify what series 1 over root n, which diverges, and why do you say it diverges? P series P equal 1/2 less than or equal to 1. That's what the worksheet looks like. Alright, anything less than that would probably lose points on a test, and some homework I would consider it skipped. Alright, so this is like a P series. Go to box 11. That's this problem. Is that like a P series? It is a P series. It's not like nothing. It is a P series. Okay? The 5 versus the 2. Right? This is a subtracted 2, and because that is not a P series. The 5 is that 2 cannot be moved out of the integral. That 5 are the series. That can be moved out of the integral. It is most definitely a P series. Not like a P series, it is a P series. And so you don't have to do any extra comparison test. You just say this blank converges or diverges. What do you say? This converges because it is a P series with P equal 5/3 greater than 1 is the great test statistic which you test against. There's a compare to 1. You follow? Alrighty then. That's statistic just like AP Stat, am I right? Questions on 127. 127 questions. Do you have any?
I had a question on 10.
Questions on 127.
One is fine.
10?
Yeah, that's pretty much.
Number 10 is a question from my mom. She asked about number 10. Okay. So the test is Monday. I will be here Monday morning if you want to go over anything, but you're going to see these reviews papers get smaller and smaller and degrade into nothingness because you need to get ready for college, and you're not always going to get a nice practice bunch of problems. You're just going to say the test is through this. No.
If we send it to the teacher,
They don't care what, they don't even care if you exist.
Oh, can you go to the test review?
what if you brag?
They are pretty poor. Maybe you gotta work, you should get that a try.
Can you actually go to the test
I
review?
can't see anything.
What's to go over? It's self-explanatory.
I just like that you went over all of it.
Over all the way, because you can't read?
No, just like a little.
If we have time, we'll go over it here. So,
I rescinded my question.
You don't want to talk about number 10?
No, I'm just kidding. I don't understand.
All right. So here, for example, as related to the test, this is an integration technique question that's a subset of ultraviolet voodoo. How do you know when you use tabular versus circular? So tabular is when something would gradually go away. With more and more derivatives, things get better and better, and you just don't want, you want to avoid having to do ultraviolet voodoo over and over and over again. That outcome tells you tabular. If I tried tabular on this, and I used either E or sine, is this ever going to happen? Is E or sine ever going to just go away and it'll get better sometime? No. If that's the case, if it just neither one ever gets better, then it's circular. And that's the case this. Now by far, the problem, once you've decided or you know that it's circular, you've got to be very, very careful with lots of little details because negatives get lost or small antiderivatives get messed up. So be neat, clean. I personally slowed myself down and tried to write this neat. I found that if I tried to write it neat, it made me go slower and I made less mistakes. It's not so much that I couldn't read my own writing, it just slowed my mind down a little bit. What do you want to let U equal, E or sine? Penny?
E.
E, okay, E to the 2x, is that a 3x? So which we're going for, huh? E to the 3x. Therefore, dv is sine of 2x, yeah? What's the antiderivative, or what's du then is 3e to the 3x dx, and v is negative 1/2 cosine of 2x. I feel like that's pretty gross antiderivative. I think I would have gone the other way, but that's okay. All right, uv then, you want to choose the one that's least likely to make mistakes. uv then is negative 1/2 e to the 3x cosine of 2x minus v du is negative 1/2 negative 3/2 e to the 3x cosine of 2x. Okay? Do you want to take those two negatives and knock them out?
Yep.
All right. All right, now we do it again. U is, be consistent. Make U 3/2 e to the 3x. The v is cosine of 2x dx. So du is now 9/2 e to the 3x. And v is 1/2 sine of 2x. Stop me if you disagree. Okay, now plug in that guy. Now because it's a positive, I don't need to put brackets around this, but if this were minus, I would put brackets around it so I distribute the negative. uv is 3/4 e to the 3x sine of 2x minus v du is 3/4. This is not what I'm expecting. Oh, v du, dum-dum. Sorry. v du is 9/4 e to the 3x dx sine of 2x dx. Are you cool? All right. Be careful then. When I add 9/4 over, I get 13/4 e to the 3x sine of 2x dx.
Wait, why do you? Oh, because
You want to, once you get that integral, that same integral you started with back, you move it over to the other side to combine with the original problem. It's important that you write the left side because you're eventually going to bring something just like it over with it. Okay? Then this should be 13/9, not 13. No, 13/4 is right, yeah? Okay, so your final answer then is 4/13 of blobbity blobbity blue plus 6. Okay, Have a great day, my friends.
Thank you.
Thank you.
I don't think,
Nice.
I don't think anyone